are recording now, and let's share the screen and let's see. Yeah. So last time we were so this was the morning tutorial session. Yeah. So this is what we were discussing last time. We introduced differentiable functions. All right. So let me start. So what is, I think it's lecture number 24 today. Let me check. 25 it is. Nevertheless, so we define what is the meaning of a function to be differentiable at a point. Yeah. And we also saw some examples. Yeah. And we were in the midst of the following result. Yeah, so let's recall where were we and what all progress had we made. So suppose that I have a continuous function f defined on closed and bounded interval a b, and this function takes values on the real line. Suppose that f is injective, right? So f is injective, so f is a bijection onto its image. Suppose that f is given to be differentiable at some point x naught in the open interval a b. Yeah. And so the derivative of f at the point x naught exists. Suppose that the derivative of f at the point x naught does not vanish. Right? Now, having assumed that f is a bijection, we can always talk about the inverse function, correct? Now, the content of this theorem is the following. Yeah, it says that the inverse function, which is defined since f is bijection, is also differentiable where at the point f of x naught, and moreover you can write down explicitly what is the derivative of f inverse at the point f of x naught. Yeah, right. So here's a small picture. You know, x naught is a point in open interval ab. F takes it to the point f of x naught. The inverse function is defined from the range of f onto the interval ab, and we are required to show that the inverse function is differentiable. Yeah. So in order to make sense out of this, yeah, in order to even assert that the inverse function is differentiable, the first thing that we need is the inverse function should be defined on an interval, at least a one-sided interval around the point of x naught. Yeah? So that is taken care of. That's what we discussed last time. That is because f is a continuous function, and a continuous function always takes intervals onto intervals. Yeah. A continuous function takes connected sets onto connected sets. In particular, the range of f is going to be in an interval containing the point f of x naught. So we can as well talk about whether or not the inverse function is differentiable at the point f of x naught. Now, in order to consider the differentiability of the inverse function, let's write f of x naught as the point y naught. And we are required to look at the following difference quotient, right? F inverse y minus f inverse y naught divided by, so in the denominator, I have y minus y naught. Now, f and f inverse are both bijections. So each point y in the range of f is corresponds to a unique x in the interval ab, which is mapped to y via f, right? So let's write y as f of x. And now what do? We take, we let y to go to y naught, right? Now, what do we do? What happens to this difference quotient if I allow y to tend to y naught? So here am I. Yeah, I am asking the question here. So what happens if I allow y to tend to y naught? what happens to this limit? Yeah, so I am considering the limit. Everybody with me up till now? Limit y tending to y naught of the following difference quotient. Yeah, we have to assert that this limit exists. Only if this limit exists, we can say that the inverse function is differentiable at the point y naught. Now, this is as we, since f is a bijection, f and f inverse are both bijections, I can write the following, right? So what do I do from this point? This is true, right? The limit of the left hand side is the limit of the right hand side. Now, what else can we do? Somebody would like to suggest something? Recall y naught is the point f of x naught. Any suggestions, please?
Ma'am, we can limit x tends to x naught.
So we would like to switch to limit x tends to x naught. That seems like a good idea because we know that the derivative of f at the point x naught exists and it does not vanish. Yeah. So the right hand side looks like we would like to get rid of this y going to y naught and replace it by x going to x naught. Yeah. And if we can do that, yeah, so as Kritika is suggesting, we should look at the following thing. We should be able to say the following. Yeah, there's a question mark here. Why is this true? Right. So we should be able to write this as, this seems like a good idea. Limit x going to x naught, x minus x naught, f of x minus f of x naught. What is achieved by doing this? So if we can assert this equality, which I have written in red ink, suppose this is true, then the right hand side is nothing but the reciprocal of the derivative of f at the point x naught. I can take that because by assumption, the derivative of f at the point x naught does not vanish. Correct? Yeah, here it is. Is that okay? Yeah. If so, then in that case, the right hand side exists and this limit is the derivative of f at the point x naught. Correct?
Yes, ma'am.
Yes. Now, how can we write limit y going to y naught as limit x goes to x naught? So we would like to replace this limit y going to y naught by limit x goes to x naught. Remember, what is it? Y going to y naught means? Yes. Yeah. Somebody wants to say something? Please go ahead.
No, ma'am, I was just saying that
Huh.
it might be possible due to f being a continuous function. That
See, what does the continuity of f say? So, Priyanshu, you're right. Something to do with that. But let's see. What does the continuity of f says? So we want here, so the limit y goes to y naught. So I'm just scribbling here just to sort of need to replace this by this, just to emphasize what is that we want to do. See, y is f of x and y naught is f of x naught. Yeah, and we want to replace. So as f of x goes to f of x naught, does x go to x naught? Is this continuity of f?
Ma'am, it should be the other way around.
It should be the other way around. Excellent. So we are talking about continuity of which function here? We are talking about continuity of the inverse function, right? We would like to say that the inverse function, F inverse, is continuous. Excellent. So do we have that? Do we have that here? Let's go back to the statement of the theorem.
Yeah.
Seems like a valid question to ask, right? We are saying that the inverse function is differentiable. We should first ask whether it's continuous or not. If it's not continuous, then there is no point, exploring its differentiability. Correct?
Yes, ma'am.
So we need the fact over here. We need the fact that the inverse function F inverse is continuous. So if the inverse function is continuous, if F inverse is continuous, then we can, without any hesitation, replace this limit y going to y naught by limit x goes to x naught. Correct? Yeah. So I'll just write that down. This is what we need. Yeah. As y goes to y naught, right? That is f of x goes to f of x naught by the continuity of the inverse function. It follows that x goes to x naught, right? So one can do this. Yeah. So this this equality here would be justified. Now the question here is, why is the inverse function continuous, right? So if that is done, we will be done with the proof. But why is the inverse function continuous? Let's go back and stare at the what is given to us. Why is the inverse function continuous here?
Ma'am, because the domain is a compact set and the F is
Correct,
1
right?
and 1 to
Excellent,
compact.
excellent. Yeah, thank you so much. So let's recall that. So recall that when we are discussing continuity and compactness, we did a result like this. That so what is that I want to say? So f from x to y be a continuous 1-1 function from a compact metric space X into Y. Then the inverse function is defined from the range of F, right? And it follows that the inverse function is continuous. So inverse function, which is defined on the range of F, is continuous. So we use that here. Over here, X is the closed and bounded interval on the real line, which is a compact set. So we use this result here to show that F inverse is continuous. Okay, so is this okay with everybody present here?
Yes, ma'am.
Yeah, all right, excellent. Yeah, so if that's the case, let's look up and take an example. Yeah, let's just go back to the statement one more time. So F is defined on a compact set. F is continuous. F is given to be injective. F is differentiable at a point x naught in open interval AB. The derivative of F at that point does not vanish. Then the inverse function is also differentiable, and one can in fact write down the derivative of the inverse function in terms of the derivative of F. Yeah. You've been sort of using this forever, but let's see, take a very simple example. Okay, so let's consider f defined as follows. Yeah, f of x is x to power n. Yeah, so n is some positive integer and x is varying over the set of positive real numbers. Okay. Now one can check that in this for this example that f is injective and f is continuous, right? Correct? In fact, not only continuous, f is going to be differentiable, right? And one can write down the derivative of f. Yeah, so you can use the first principles, meaning the difference quotient, and look up the limits and things like that. To compute the derivative of f, it turns out to be n x to power n minus 1 for x in the interval. Yeah, so it's differentiable at each point on its domain, right? And what is the range of f? The range of f is going to be the interval 0 to infinity, correct? So if I pick some point x naught in the interval 0 to infinity, and let's write y naught as its image under f. Then I can apply this theorem to write down to assert that first thing, that the inverse function is differentiable at the point y naught, and the derivative at the point y naught is given as the reciprocal of the derivative of f at the point x naught, which is n times x naught to the power n minus 1, which is in terms of y naught, this is n times y naught to the power n minus 1 by n. Correct? Is that okay? Is everybody with me so far?
Yes, ma'am.
Any questions? Okay, so then I should throw a question at you. See, the domain of definition of f in this example is not compact. Then how do I apply this theorem here? Right? It's not bounded, right? Neither it's closed nor is it bounded. So how can I apply this theorem here? And if you remember, so compactness is used there. Compact is used in what I've written in red ink here, right? To assert the continuity of the inverse function, which is very, very important in the proof. And we have seen that, compactness cannot be dropped out of this. Compactness is essential to assert this. So how do we apply this theorem here? Can somebody help me out? Any suggestions? See, here is what can be done. Although the entire interval 0 to infinity is not compact, let's look at, so suppose that 0 is here, right? Let's look at the point x0. X0 is some point in open interval 0 to infinity. Yeah. What you do is you pick the point x0 by 2, right? And let's look at 2x0 here. You can apply this result to f restricted to the interval x0 by 2 and 2x0, for example. Now this is a compact set, right? Is that okay? Now this is a compact set where the function f is continuous 1 1, and this set contains the point x0. You apply this the previous theorem to this set and not the entire open interval 0 to infinity. You get the same conclusion. Is that okay? Does everybody realize why is this needed?
Yes, sir.
Yes, and x0 by 2, 2x0, this is nothing unique about it. You just pick something which contains the point x0 and it's compact on the real line. Yeah, so this is one such example. Is that okay? Is that a yes with everybody present here? Any questions, please ask. Somebody is still doubtful, please ask.
Ma'am, could you please repeat once again?
See, all I'm trying to say is, see, this we cannot apply this theorem directly, right? In this example. Why? Because the domain of definition of f in this example is not compact, right? And as we saw the proof, compactness plays a crucial role, right? Is that okay? That bit is okay?
Yes, ma'am.
Yes. Okay. Now, so how do we fix it? So all I'm trying to say is, let's see, we want to say that the inverse function is differentiable at the point x0. Now, instead of working with f defined on the entire interval 0 to infinity, you pick a compact set around the point x0 where f is defined. One example is that you work with the interval x0 by 2 to x0. Now, this is closed, bounded, so this is a compact subset of R. Now, this interval contains the point x0, right? You apply the previous theorem to f restricted to this interval. Now, f is a 1 1 continuous function defined in a compact set. So, the inverse function, f inverse, would be a continuous function wherever it is defined, just the range of this little interval, x0 by 2 to x0, right? But that doesn't matter. That set contains the point f of x0, right? And the rest of it goes through, right? Exactly this. So all I'm trying to say is, instead of applying the previous theorem to the function f on the interval 0 to infinity, one should apply f intelligently on a smaller subset, just to make sure that the domain of definition is compact there. Is that okay?
Yes, ma'am.
Yes. Is that a yes with everybody? And all I'm trying to say is, there's no uniqueness here. You just pick any compact set containing the point x0. That's it. It should work. All right. Everybody with me so far?
Yes, ma'am.
Okay. Excellent. Okay. So having established this, this is very, very useful in practice. We will move on to the next topic, which is the mean value theorems. So before we can take up the mean value theorems, here are some definitions which we would possibly need. Okay. So here's a definition. So let X be a metric space and let's consider a function f defined on X taking values on the real line. Yeah. So let's consider a function f, a real valued function defined on X. Right. We say that this function f has a local maximum at a point P. Yeah, local or relative maximum at a point P of X if the following is true. Yeah? If there is a delta such that what happens? The following inequality is satisfied. Yeah? So f of X cannot be bigger than f of P, and this is true for all X in this delta neighborhood of the point P and all points in X. Yeah. So f takes the maximum value at the point P locally. Yeah, loosely speaking. Is that okay? Yeah. And a relative minimum or a local minimum for a function can be defined analogously. So I'll just write that down. Yeah. So for example, if my function looks like yeah, so this is not very nice. Let me just erase this. If my function looks like this, then what can you say about this point? Or maybe, I'll just introduce more curves here. We make it more steep. So what can you say about, let's label these points. Let's label this point as P1 and let's label this point as P2. And so what can you say about the points P1 and P2 in terms of the definitions that we have just learned? And to my mind, f has a local maximum at a point P1 and a local minimum at the point P2. Is that correct? Is this okay?
Yes, ma'am.
Yes. All right. Now, why is there sudden interest in local maximum minimum? What have they got to do with differentiable functions? So here is a result that links them together. This is again perhaps something that you might be already familiar with. Yeah? So suppose that f is a real valued function defined on a closed and bounded interval a b, and let's pick a point p in open interval a b. So if f has either a local maxima or a local minimum at the point P in the sense defined above, then we can say something more. Yeah, if f has either a local maxima or a local minimum at P, okay, and furthermore, if we are given that f is differentiable at the point P, means that the derivative of f exists at the point P, then it turns out that the derivative of f at the point P has to vanish. So if f has a local extrema at an interior point, then assuming that f is differentiable at that point, then the derivative has no choice but to vanish at that point. Yeah. So what does it mean to say that the derivative is vanishing? That the slope of the tangent line to the graph of f at the points, as is evident in this picture, at the points P1, FP1 and P2, FP2 is 0. Yeah. So the tangent line is parallel to the x-axis at the points of local maxima and local minima. Correct? Is that okay? So let's provide a proof. Everybody with me up till this point? Is that okay with everybody? Okay, any questions, please ask. All right, let's go on, assuming that there are no questions. So suppose that f has a local maximum at the point P. Yeah, so the proof is similar if f has a local minimum at the point P. So let's just assume one of them and go ahead. Okay. So saying that f has a local maximum at the point P by definition means that there is some positive delta such that the following inequality is satisfied. Yeah, f of x minus f of p is at most 0 for all points x in this delta neighborhood around the point P intersect the interval AB. Yeah, correct? Is that okay? Now, what are we required to show? We are required to show that the derivative of f at the point P vanishes. Yeah, we are given that the derivative of f at the point P exists. So no matter how we approach the point P, since the derivative exists means no matter how we approach the point P, if you look at the difference quotient fx minus fp by x minus p, that should tend to the same limit. Yeah? So we will exploit this thing, and we will let's see what it gives us. So let's take xn be a sequence of points in p plus delta converging to p. Yeah. So what am I taking? I am taking a sequence of points tending to P from the right. Right. Now, so let's look at the difference quotient f of xn minus fp by xn minus p. Yeah. So if I take the limit as n tends to infinity, what is this limit? This limit is just the derivative of f at the point P. Correct? We are given that the derivative of f at the point P exists. No matter how we approach the point P, the limit fx minus fp by x minus p should exist and tend to the same value. Now, what can we say about this difference quotient? See, what is that we know? P is a point of local maxima. Yeah. So which means that f of x minus fp is negative no matter what. Right. So in this difference quotient, the numerator is negative. And how about the denominator? Xn minus p? The denominator is positive because I am taking xn to be the points of xn's are defined in such a way. Let me draw a little picture if that helps you. Xn's are, so let's say p is here, p plus delta is here, and p minus delta is here, and here are xn's. Yeah, xn's are points tending to P from the right. Huh? So what is that you can say about the denominator? That the denominator is always positive, which means that this difference quotient is almost, is always negative, and so would be the limit. Is that okay? On the other hand, if I take a sequence of points tending to P from the left, yeah, so let's do that. So let yn be a sequence of points tending to P from the left. Then, and look at this difference quotient again. Yeah, so then let's look at the difference quotient f of yn minus f of p yn minus p. Yeah, now this limit as n tends to infinity, since f is differentiable, this exists and equals the derivative of f at the point p. However, what can I say about this limit? See, the numerator is always negative. Why? Because f has a local maximum at the point p by assumption. And the denominator, since I am taking the points yns to approach P from the left. Yeah, so in this picture here are yns. Since I'm taking yns to approach the point P from the left, the numerator is, the denominator is, what happens to the denominator? So that is also negative. So which means that this difference quotient is always positive no matter what. And the same is going to be true about the limit also. Yeah. So if you put together these two inequalities, this proves that the derivative of f at the point P must be 0. So let's write this as inequality A and write this as inequality B. So combining A and B gives that the derivative of f at the point P must be 0, and that's all. We are done. Is that all right? Everybody with me? Any questions? Comments, suggestions? Okay, so shall we move on to the next thing, if this is okay?
Yes, ma'am.
Okay, excellent. Having understood this, let's go on to the first mean value theorem. So what is it says? So suppose that f is defined and continuous on closed interval a b, and differentiable on open interval a b. Okay. So differentiable a b will be there except at the endpoints a and b. Yeah. So if f takes both a and b to 0, then there is a point in the open interval AB such that the derivative of f at that point is 0. Yeah. So what is this saying? This theorem, is telling us the following, that so let me draw a little picture here. So suppose that A is here and B is here. Yeah. So FA is also 0, so FB is also 0. So one possibility is that the graph looks like this. Okay. So what is it saying? That there is a point C in open interval AB such that the slope of the tangent line to the graph of f equals 0. Yeah. So in this picture here is the point C. Yeah. The slope of the tangent line to the graph of f. Now what is it saying? Saying it one more time, there is a point on the curve on the graph y equal to fx whose tangent line is parallel to the line segment joining the endpoints of the curve, right? See, I would actually be careful in this sense here. The picture that I have drawn here, the function f is not differentiable. Yeah. So let me sort of smoothen it a little bit to make it differentiable. Yeah. Is that okay? Does everybody understand this? Actually, the tangent line to the point C here does not even exist. So let me, because f is fails to be differentiable here. There was a kink there, right? So something like this would work. Is that okay?
Yes, ma'am.
Yes. Okay. All right. So how do we do this? Okay. So f is already assumed to be differentiable everywhere except possibly endpoints. So let's see. We are required to show that the derivative of f vanishes at some point on the open interval AB. Right? So let's see. If f is identically 0, then there's nothing to be done, right? Then any point C in open interval AB would do the job, right? Because the derivative is also going to be identically 0. Let us suppose that f is not identically 0. So without loss of generality, we may suppose that f is strictly positive at some point on its domain. Yeah. So let's write that. Otherwise, we may suppose that without loss of generality. Yeah, so this is saying that there's no special assumption here. This can always be done. Without loss of generality, that f of x is strictly positive at some point x. Yeah? So x is, by assumption, some point in open interval AB. Yeah, because f of a and f of b are both 0. That's given to us. All right. Let's see. So f is defined and continuous on closed and bounded interval AB. So I'm going to apply the extreme value theorem here. Yeah. So what does that say? The extreme value theorem says that in this setting, that the supremum and the infimum of f are actually realized. Yeah. So I'll just write that down here. Since f is continuous and defined on a compact set, so f is continuous on a compact set, it follows that the supremum of f is realized at some points on a domain, right? It follows that there is a point C in the interval AB such that the supremum of f on the interval AB is realized at the point C, yeah, which means that at the point C, f of C is the maximum. Okay? See, what am I trying to do here? I have to find a point C where the derivative of f vanishes, right? So I am going to apply this little observation that I did, yeah, that if C is a point of local maxima or minima and f is differentiable, which it is in our case, then the derivative of f at that point has to vanish, right? So I am trying to locate local maxima and minima for this function f. Now I have no control. How do I isolate local maxima minima? So I am trying to pick the global maxima and minima, and I'm going to see what happens then. So this is what I'm doing. By the extreme value theorem, the global maximum of f is realized at some point in its domain, right? Now let's look at FC. Now can C be the endpoint A or the endpoint B? Can that happen? Can that happen? Somebody wants to say something? Please go ahead.
No, ma'am, it can't be endpoint.
Why is that? You're right. Why is that?
Because it will not be differentiable then.
So then what happens? We can still consider, anyways. So, but where does differentiability come into the picture here? See, I agree with you. In order to show that C is a local maxima or a local maxima, we need to show that C cannot be the endpoints A and B, right? Now, how do we do that? is what I'm trying to say here. See, the extreme value theorem says there is some point C, I don't know where it is. It can be the endpoints also, somewhere, at some point C in the domain of definition of F, the maximum or the supremum of F is realized. Now, with the current assumption, I say that C cannot be the endpoint A and B. Why is that the case? Can somebody please
Ma'am,
help
because we
me?
have
Go ahead, go ahead.
Ma'am, because we have considered at some x fx equals to 0 and fa and fb are equals to 0.
Right. So since FA and FB are both 0 by assumption, and FC is where the maximum is realized, yeah. So in particular, f of C is going to be at least as big as this point f of x, yeah. So let me look at f of x dot just to fix things. Is going to be at least as big as f of x naught, which is strictly positive. C cannot be the points A and B because FA and FB are both 0, right? We must have C in open interval AB. Is that correct? Yeah. And now, so the maximum of F is realized at the point C. Yeah. Now, recall that, so I'll rather say that hence, so what is that we have? Once we have shown that C is in open interval AB, I say that we are done. Hence, f of x is less than equal to f of C for all points x in the interval AB, and C lies in open interval AB. Yeah? So this is enough to show that f has a local maximum at the point C. And we are done. So let me give the previous theorem some name. So the previous result tells you this one here, which we just did. So theorem 1 today of lecture 26. So theorem 1 now implies that the derivative of f at the point C must vanish. Sorry, where am I? What am I doing? Here. So theorem 1 now implies that the derivative of f at the point C must vanish, and we are done. Is this okay with everybody? I just scroll back to the previous page where we were. In case you have some questions, please ask. Yeah. So we knew that f, the derivative of f, if f is given to be differentiable, vanishes at points of local maximum minima. We don't know how to get them, so we started with global maxima, tried to prove that is indeed a local maximum also, and we are done. Is that okay? Any questions? Okay, so assuming that there are no further questions, having proved the first mean value theorem, let's record a corollary to the first mean value theorem, which is due to role and called as the Rose theorem. So these assumptions are very similar to what we had in the first mean value theorem, except the following thing. So suppose that f is a function defined on closed interval a b, real valued. So suppose f is continuous on closed interval a b and differentiable on open interval AB, yeah, much like the assumptions in the first mean value theorem. So in the first mean value theorem, what did we have? That FA and FB are both 0. Here we don't have that. All we have is that FA equals F of B, right? So then the Rolle's theorem says that there is a point C in open interval AB such that the derivative of f at that point vanishes, right? So the conclusion remains the same. So suppose this is the point A and this is the point B, yeah? So if A is equal to B, so maybe the graph looks like this, something like this. So at some point in open interval AB, the slope of the tangent line to the graph is, so this is the slope of the tangent line to the graph, is parallel to the line segment joining the endpoints of the curve. So in this case, it's going to be parallel to the x-axis, right? And you know, this is an immediate corollary to the first mean value theorem. How did you deduce Rolle's theorem from the first mean value theorem? You construct another function g. So apply the first mean value theorem to the following. So I'll say first mean value theorem to the following function. How do I define g? I say that let's define g as the following. So the function in the first mean value theorem assume the value 0 at the endpoints, right? So what do? I say it is f of x minus f of a. Right? Everything else remains unchanged, right? So then g would be continuous on closed interval AB, differentiable on open interval AB. G and GB would be both 0, and there would be a point C in open interval AB by first mean value theorem where the derivative of g would vanish. So that would exactly say that the derivative of f at that point would vanish. Is that okay? Everybody with me up till this point?
Yes, ma'am.
Yes. Okay. All right. Having done the Lagrange's mean value. Yeah. Sorry. This is the Rolle's theorem. Now the next thing is the second mean value theorem, also called as the Lagrange's mean value theorem, or the mean value theorem, whichever you want to call it. Second mean value theorem. Okay. Here is the statement. So again, f is defined and continuous on closed interval AB. And differentiable on open interval AB. Then there is a point in open interval AB such that the derivative of f at this point C is given as follows. So what does the right hand side represent here? Let's see. Yeah. So suppose that, so this is the x-axis, this is the y-axis. Let me draw, so there's no assumption on if the values, the function f takes at the endpoints a and b. So let me draw something like this, right? So suppose, let me be a little bit careful. This is not a function. Yeah. Let me draw something like this. Right. So suppose that this is the endpoint B, and smoothen it out a little bit because I have assumed that f is differentiable on open interval AB, which means that there should be no kinks in between. Yeah. So this is A, and suppose this is the point B, right? So f of A in this picture is 0 and f of B is some positive value, right? So what does the right hand side here? The right hand side here denotes, what does it denote?
And slope of the line joining A and B.
Slope of the line joining AFA and BFB, right? So let's look at this line segment which joins AFA and BFB. So it is saying that there is some point in open interval AB such that the slope of the tangent line to the graph of f at the point C must be the same as the slope of the line joining AFA and BFB. Correct? Yeah. So in this picture that I've drawn, there actually 2 points, right? Is this okay? Is everybody with me?
Yes, ma'am.
Yes. So let's write the argument. Okay. So let's define a new function here, g. Right. So what will I do? I will look at g as I will define as the difference of fx and Lx, where what is Lx? Lx is the function defining this chord joining the 2 points AFA and BFB. Yeah, so let me try to write down the equation. So I have AFX and AFA and BFB, right? So one point is this, and the slope is given by this, right? FB minus FA by B minus A, and times x minus a. Is that correct? as long as I know one point and the slope of the line, then I can write down the equation of that line segment. Correct? Yeah, and where is x? X is in the interval AB. Yeah. Yeah, so what is G here? G is actually the signed vertical distance from the graph of F at the point X to the graph of the line segment joining AFA and P. Yeah, so this is G, right? This distance is G. Correct? Is that okay? Right. So since f is continuous everywhere on closed interval, so is G. And since f is differentiable everywhere on open interval AB, so is G. And what happens to the function G at A and B respectively? What is G of A and G of B? What happens to G at the point A and B respectively? It is 0, right? Is that correct? So that means that G satisfies the hypothesis of the first mean value theorem, right? Which means that it follows from the first mean value theorem that there is a point C in open interval AB such that the derivative of G at that point vanishes. So what am I writing here? It follows from the first mean value theorem that the derivative of G at the point C vanishes for some C in open interval AB. Right? But what is the derivative of of G at the point C? The derivative of G at the point C is the way the function G is defined is exactly the derivative of f at the point C minus whatever we need, right? FB minus FA by B minus A. Is that okay? And we are done. Is everybody with me up till this point?
Yes, ma'am.
Yes? Okay. All right. So, there is one common thread in all these mean value theorems, which I would like to emphasize, that all these mean value theorems say the same thing, right? They are saying that there is a point on the curve whose tangent is parallel to the line segment joining the endpoints of this curve, right? And yeah, and that's it, right? There is one more in this string of ideas, which is the Taylor's theorem, right? So in order to understand what theorem is saying, let's do the following first. Towards Taylor's theorem, so this is what we know so far. So if f, so there's an observation on this side. So if f is a function defined on the interval AB, closed interval AB, and suppose that it is differentiable everywhere, So saying that it is differentiable on the interval a b means the right hand derivative of a and the left hand derivative of b exist. So left hand derivative at the point a, the right hand derivative at the point a and the left hand derivative at the point b, and exists, and f is differentiable on the open interval a b, right? So suppose this is the case, suppose f is differentiable on the interval a b, then one can talk about the function which is the derivative of f. Now the derivative of f is another function which is defined everywhere on the interval a b. Now suppose further that the derivative of f, which is another function, this is again differentiable on a subset E of AB. Yeah. So I'm saying, and if the derivative of f is furthermore differentiable on a subset E of the interval AB, then what can you do? Then you can talk about, and you can differentiate the derivative of f. Yeah, you can differentiate this function one more time. Yeah, then we can define the following. So this is a new notation that I am introducing. This is so I already have this function and I am taking the derivative of this function. Where is this defined? This is defined everywhere on E, right? And what is this called? This is called as the second derivative of f on E. So similarly, you fix a positive integer n and you would like to consider the nth derivative of f at that point. Yeah. So let me write this down. And then maybe I will see this. So more generally, for n any positive integer, one defines, what is this symbol here? This is the nth derivative of f. How do you get this? You define it iteratively. You consider the n minus 1th derivative of f and differentiate it. Where is this defined? This is defined on a set E if the n minus 1th derivative of f is defined on an interval containing E. So I'll say that one more time. So in order for the nth derivative of f to exist at a point x, the n minus 1th derivative of f must exist in a neighborhood of x, at least in a one-sided neighborhood of x. So maybe it will help if I write it down. Otherwise, this may seem like too much being thrown at you at one go. Yeah. So let's just go slowly, and I'll write down whatever I said. So in order for the nth derivative of f to exist at the point x naught, it is important and it is required that the n minus 1th derivative of f, this function is exists and is defined on a neighborhood of the point x naught. At least we need it to be defined in at least a one-sided neighborhood. Yeah, you can talk about the left-hand derivatives and right-hand derivative, whichever is the case may be. So we need two things. One, the n minus 1th derivative must be defined in a neighborhood of x naught, and the n minus 1th derivative must be differentiable at the point x naught. So I'll say and the n minus 1th derivative of f must be differentiable at the point x naught. Now let's do it one more step. Since n minus 1th derivative must exist, let's look at the first assumption. Since the n minus 1th derivative must be defined on a neighborhood of the point x naught, what does it mean? It means that the n minus 2th derivative of f must be differentiable in that neighborhood. That things like that. Is this okay? Is this okay with everybody?
Yes, ma'am.
Okay. So let me maybe try to see what is that we can say about the Taylor's theorem. Yeah, suppose that I have a function which is differentiable n times at a point x naught. Yeah. So let's just do an observation. Suppose f is differentiable n times at some point x naught. Okay. All right. So which means that f of x naught exists, right? The first derivative of f at the point x naught exists. The second derivative of f at the point x naught exists, and all the way the nth derivative of f at the point x naught also exists. This is given to us, right? So let me do the following. Yeah, I'm going to look at the following polynomial. Yeah, so I'm going to look at f of x naught plus the derivative of f at the point x naught, x minus x naught, plus the second derivative of f at the point x naught times x minus x naught square by factorial 2, and so on all the way the nth derivative of f at the point x naught, x minus x naught to the power n by factorial n. Now this is a polynomial, right, of degree n. Yeah, so I'm going to call it p, yeah, and subscript n. Now, what is the property of this polynomial? This polynomial has the property that this polynomial, and a polynomial is infinitely many times differentiable. There's no problem. Yeah. So a polynomial, this has a property that this polynomial and its derivatives up to order n agree with the function and its derivatives up to order n at the specified point x naught. Now this polynomial Pn is called as the nth Taylor polynomial for f at the point x naught. Let me write that down. Okay, I think with this information, let me just state the Taylor's theorem, and maybe I'll say a word as to what is this theorem actually telling you. So let's fix some positive integer I, sorry, n. And suppose that I have a function f defined on interval a b, right, such that the function f and its derivatives up to order n. Yeah, so f derivative, the second derivatives up to order n, the nth derivative, all of these are defined and continuous on the interval a b. Yeah. So all derivatives of the function f up to order n exist and are continuous on the interval a b. Yeah. And what about the n plus 1th derivative? The n plus 1th derivative exists on open interval a b. Yeah, the n plus 1th derivative need not be continuous, but what we know is that it exists. Then we can do the following. So let me write it in this form. Let's fix the point. Let's fix a point x naught in this interval a b. Then for any x in the interval a b, let's look at f of x. F of x, one can write it in the following form. Yeah, so it is f of x naught plus the derivative of f at the point x naught, x minus x naught. So what am I writing here? I am writing the Taylor polynomial, the nth Taylor polynomial of f at the point x naught. Yeah, so let me do that. So this is x minus x naught to the power n by factorial n. This is a polynomial. So, you know, all of these derivatives are evaluated at x naught. Please note that. And then you have the n plus 1th derivative of f evaluated at some point c. And what is this c? C is some point where between x and x naught. Yeah, so depending on you know, whether x is bigger or smaller than x naught, c lies between x and x naught. So I will not write interval notation. For some c between x and x naught. See, so what is this saying? This is saying that, you know, let's just recall, you know, this term here is exactly the nth Taylor polynomial for f at the point x naught, right? Now, what have I done here? We have written the function f as a polynomial, right? Plus another function Rn, yeah, where what is Rn? So this is the Rn, yeah. So this is called as the remainder term. This is the derivative form or even the Lagrange form of the remainder, right? Now this remainder term involves this c, which is unknown, right? So this is saying that if you know that the function f, you know, where is the statement, is n times differentiable. So the all possible derivatives of f up to order n exist and are continuous on the interval AB. The n plus 1th derivative of f exists everywhere on the interval AB. Then what is that this theorem is saying? You can approximate the function f by a polynomial of order n. And Rn is the remainder term. It is telling you what is the sort of quality of your approximation. What is the error involved in this approximation? The higher the n, the better the approximation. Now, f need not be a polynomial. F is any arbitrary function. Yeah, so this is saying something about the polynomial approximations. So maybe I think I'll just stop right here for today. And next time we meet, we will start with some sort of applications of Taylor's theorem, examples of Taylor's theorem.